Hi everyone, Mr. Lee here. In this video, we're going to go over Coulomb's law. Now, this is a very specific scenario. This is Coulomb's law for an object that is hanging. And for the sake of this video, we're going to say that the hanging objects are balloons. Now, they can be anything from very lightweight objects, but we're going to use balloons today. All right, let's begin. So to start us off, let's do a quick little sketch. Up here, you see a horizontal line that just represents our ceiling. And we have two spheres down here that can represent my balloons. And these balloons are attached by two strings. And because of Coulomb's law, they are repelling each other, which means that they have the same charge. Up here, you can see that there is a angle symbol. They're separated, the strings are separated by an angle, and I just drew a dotted line straight down the middle to show you that if I were to bisect that angle, we will get two angles of the same magnitude. All right, so we have two of the same angles right there. Okay, so when we start this, there's a couple of things that we should keep in mind. Now, if we were to do this lab in like the real world, we would see that the balloons are a very spherical object, or they're an object that takes up volume, right? But for the sake of our problems, it's easier to not view the balloons as a giant object, but rather as a point charge, meaning that this red dot and this blue dot, instead of a spherical object, we just think of it as a point along this coordinate plane that has a certain amount of charge. Trust me when I say it is easier to view it that way. Now, another way that you could view it is you would view the middle part of the balloon or object as the location of all the charges. So we would imagine that the charges are located right there and right there. All right. But for the sake of this, we can imagine that the balloons do not, in fact, take up space, but they are rather existing there as a ball of charge. Okay. So in order to solve these problems, we're going to be utilizing what we learned from the mechanics course. We're going to first start off with a free body diagram. So the reason why we need to do this is because we have a lot of different forces that are going on here. We have gravitational forces and we have the electric forces. And because the two forces are under the big umbrella of forces, we can actually use the two values to do our math. Okay? So what I want to do is I want to break it down. Let's break down the balloon on the right. Let's draw a free body diagram. I'll draw this free body diagram in a different color. Let's do green here. All right. So the first force that I want to draw is the force of gravity going down. Okay, because we are existing within the gravitational field. This in fact does exist. Now, my forces, my vectors, are not being drawn to scale, meaning realistically this force, I drew it as pretty large, but in actuality it's going to be pretty small. And the reason for that is the masses of these objects will be very, very, very small. Okay, all right, so we have a force of gravity going down. Okay, and we can say that because these two balloons have the same charge, and for the sake of just making things clear, we'll say that both Q's have a negative charge. Okay, they both have negative charges. All right, and so that means that this balloon will be pushed to the right with a electric force, or a electrostatic force being pushed to the right. All right, and the last force that we can include is this force of tension right there. This force of tension. Okay, so we're given a free body diagram here, and what we can do is I just want to show you how to really set up the problem, so that if you're given numbers or if you're given a lab scenario, you should be able to solve it just by going through these steps. All right. Okay, so here we have an angle. I'm going to call this bisected angle here. Let's call that theta. And I'm going to draw another dotted line down here to show us that we are, in fact, dealing with a triangle. And let's call this angle here, we'll call it phi. Okay, we'll call it phi, just so that we have two different kinds of angles. All right, and of course, right here we have our right angle because we do have a right triangle. Now, the reason why I did this is so that we have this tension T here, and that tension T has components both in the X and the Y axis. So what we can do is we can break down that tension T. So I'm going to redraw my free body diagram over here. Let's do black. All right. We can say that we have FE, right? And here we have FG. And here we have T, but because we have these two vectors, we can break it down like so. All right. Now I'm going to label this as theta, and I'm going to label this as phi. All right. Now it's important to know, it's kind of hard to see right there, but I'm going to redraw my vector heads in a different color so that you do in fact get to see it, right? Because vector heads are very important here. Now, with this, we can come up with a net force equation. We can say F of y is equal to Ty, positive because it's going up, minus F of g, right? And all of that is equal to ma. The cool thing is, for any kind of scenario, these are usually stationary, so the acceleration will be, in fact, 0. And so what it turns out to be is that the tension in the y-axis is simply equal to the weight of the object itself. And we could break this down. You can say that Ty is, I'm going to use phi. If you want to use theta, that's fine as well. But Ty, actually let's just use theta, right? So it is T, this theta here. I'm going to highlight it so you can see what I'm pointing at. That theta there is adjacent to Ty. Let's label Ty. This is Tx. And so whenever it's adjacent, we say that it is cosine of theta. Okay, so T cosine of theta is equal to mg, right? And whatever the problem is solving for, you can find it there. All right, now f of x, we have fe in the positive direction, positive only because it's moving to the right, not because it's attracted or anything like that. And of course, we have negative tx, negative because it's pointing to the left. And of course, Newton's second law is all equal to ma. Now, once again, because these balloons are being suspended, they're not moving, we can say the acceleration is 0. And so that turns out to be Fe is equal to Tx. Okay, so let's break this down. If Ty was cosine of theta, if I take a look at my drawing, excuse me, to my left here, I'll do this in a different highlighter. We can say that Tx here is opposite of angle theta. And because it's opposite of angle theta, we can use sine. So the tension sine of theta is equal to F of E. And F of E, we just replace it with Coulomb's law. K, Q1, Q2, all divided by R squared. And we can use that formula to determine whatever we would need. Now, just as a way to go back, we can also do the same for the other balloon. You will go through the same process by drawing the free body diagram. Now, a couple of things that they might throw at you is if you are given a scenario like this, one piece of information that the problems might give you is the separation distance between the two charges. Okay, so the separation distance between the two charges would be r, and that would be the r that we would put in the Coulomb's law. Now, the only other thing that you could really look out for is sometimes with this r, you have to be careful when you are dealing with the distance for the triangles, okay? Just as a way to really keep that in mind. So for example, if you are given not the distance between the two charges, but rather, I'm going to do this in a different color. Let's say you are given the length of the string. Okay, so if you're given the length of the string, what you have to do is you have to actually find the distance between the bisected angle or the connection point. Okay, you have to find that length right there. And once you find that length, let's say we'll do, I'll call this Rx, right? So we're trying to find Rx based on this hypotenuse, right? So we can use our trig identities. So for example, if up here we have theta, we can say that Rx is equal to the hypotenuse times, now if this is theta and Rx is opposite of Rx, we say that it is in fact a sine of theta, right? So that'll be the distance between the balloon and the midpoint. Okay. Now, if you want to actually find the separation distance between the two balloons, what we would need to do is we would multiply the Rx by 2. So 2Rx would give us the entire separation distance, R. All right, so those are the kinds of little things that you should look out for. Another way that the problems can be a little bit more trickier, instead of giving you this the individual angles, they could in fact give you this angle from the ceiling right here. Right, they could give you that angle, or they could just give you the angle the two strings make as a whole, instead of giving you the bisected angle. All right, but the way that you can solve these problems are always going to be the same, which is draw a free body diagram, create a net force formula, and go from there. All right, I'll see you later.